Hello and welcome to our lecture on Postgres full-text indexes. So you can get this material online, the PowerPoints. I've only got PowerPoints for the diagrams in case you want to reuse them, because I basically switched my style in this particular lecture from doing it all in PowerPoint to taking what I usually build as my lecture notes and just recording those and giving you my lecture notes rather than making lecture notes, turning them into PowerPoints, and then giving you the PowerPoints. I hope that you will find this to be more useful. I'd be curious if you like this format compared to the all PowerPoint format. So you can get these materials online and add whatever you want. So first I want to talk about row layout. And we've been talking about the create table and how schemas and how important it is to be precise about, if this is a short text column or a long text column, et cetera, and that schema becomes a contract because that's the way that Postgres can very efficiently store the data. And the amount of data that you scan is the sort of the thing that determines your performance. And so now I want to talk a little bit about how a schema is represented on disk. So here we have a little tiny a messages table, one we've used for a couple of examples, where we have an email message, a timestamp, and then some relatively large bits. And you see that, the ID is small. It's exactly 4 bytes of memory, and the timestamp is 8 bytes. And then these other things are kind of long, and we don't exactly know what their length is. Now remember, we can insert, and then we can update these. And so you might have an email address that's 4 characters or 20 characters, and replace it with an email address that's 10. The size of a record can go up or can go down based on updates. And when we modify data, we don't want to rewrite the entire file, because that's let's just say a minimum a gigabyte file. It takes about 2 seconds. Even on the fastest hardware, writing or reading a gigabyte takes, several seconds of time. And so Postgres organizes its disk files with free space on them, and they're organized into blocks of fixed length. And by having blocks of fixed length, typically 8K, 8192, 8K blocks, they're able to sort of compute a block offset really easy, so they don't pack the blocks in either. They make fixed blocks. So they can read the entire block into memory. The block is often a unit of locking. The block is often a unit of caching. So one of the things the database does is actively use blocks end up sitting in the memory. And so if you're hitting a bunch of queries at the same time and they keep reusing little blocks of files, then those blocks will stay in the memory. And so everything that the database environment is doing is making it as efficient as it possibly can be. And so for transactions, which we briefly talked about, they're often the unit of locking. So we think of locking a row, and a block has, somewhere between 50 and 5 and 50 rows maybe, or even less than 5, maybe 2 and 50 rows, but it doesn't matter. So let's take a look at the shape of a block, right? So here we have an 8K block, and remember that 8K blocks are, they're all 8K. And so they're a place on disk, and they're stored one after another on disk. And within the block, there's some header stuff and other things that's in there. But the basic idea is the rows are inserted into this block sort of from the back to the front. Now each of these rows has columns, some of varying length, and different rows have overall different length, and the columns are in there. So then you insert another one, and you insert another one, and the rows grow from the end of the block forward, and then all they have is these offsets are probably 2 to 3 bytes, probably 2 bytes. And what they are is they're just like an array of where within that block the start of a row is. And so they're small, the whole block comes in, and then you can quickly go to each row, you can read them in order, you can read all of them. So, and then the middle here, which is really not to scale on my picture, is the free space. So you have growing from the end of the block the rows, you've got growing from the front of the block, you've got the offsets. Now the rows are generally way bigger than the offsets. Now, think about this from an update perspective, where we are, so if we were going to just take this a row, and there's 10 characters, an email address, and we're going to replace it with a 15-character email address. We can shift just a little bit of data, 5 characters. We're going to shift everything 5 characters to the left, and then we make 15 characters, and then we put the new email address in where it belongs. And then we just rewrite the whole block, and we've lost some of the free space. Same thing would happen if we rewrote an email address with a smaller email address. We'd shift everything. Actually, we might not shift everything at that point, but the point is we can make small changes to this. Now again, in my picture, free space is not to scale, because you don't want to make free space. In my picture, it kind of looks like it's 70% of it. This is a block being filled up. But the idea is that we can make tiny little modifications and then change these offset values and then rewrite the whole block to disk. The whole block's read in, we fiddle with it in memory, which is a very cheap operation, and then we rewrite it back out to disk. Now you might say, well, what's the best idea? A block size. And they go round and round and round, and there's a lot of things in Postgres where just accepting the default is probably what you want to do. And so 8K is generally the default. If you have a block that's too small, and then your rows don't fit well, you sort of fit like one row in a block, then you got kind of a wasted free space. If you have too large of blocks, then you're pulling too much information in and out just to like read one row, and you start using up all your memory, your caching. You can, if you have 8K blocks or 16K blocks, you can cache 50% of the blocks, 50% fewer blocks if they were 16K. And so you can go read up on that. Say, what's the best, go Google and say, what's the best block size for Postgres? And they'll tell you that it's probably 8K, and the next best block size might be 4K. And it has to do with the fact that solid state disks, unlike spinning disks, so spinning disks have a rotational delay, and then once you get to the data on the spinning disk, pulling in 8K is smarter than pulling in 4K, because the rotational delay is by far the greater consideration. In SSD disks, there is no rotational delay. And so then what happens is the thing that dominates is the actual amount that you transfer. And so that would advocate for smaller block sizes on SSDs and larger block size on hard drives. The problem is if you make the block sizes too small, then you get fragmentation, and you can't do some of those dynamic things where you're either inserting a new row, or you're taking some data, or you're updating a row. And so the too tiny of a block size, and then you get either too much free space because you can't fit enough rows in a block, or you get too little free space, and then you pack 2 rows in and you've run out of space, and you do an update, and then you got to move stuff all around in your database, and it's not good. So there's a lot of different ways to think about this, but the key point to take away from all of all this is that we read entire blocks into memory. So we don't really know where a row is exactly on disk, but we do want to know where a row is in a block. We know that this row is in this block, then we read the block in, and then we scan through the block and then find the row. So we can't go straight to a row, we can go straight to a block. So indexes, which is what we're really talking about now, indexes are basically a set of hints that map from a row that we're looking for to which block those rows are in, and that's what we'll talk about next.